Dear learner, I welcome you all in MOOC course on Principles of Electrical Sciences. Myself, Dr. Sanjay Agrawal, Associate Professor in Electrical Engineering, School of Engineering and Technology, IGNOU, New Delhi. In previous lectures, we have discussed resonance condition for RLC series circuit. In this session, we are going to discuss parallel RLC circuit and we will also discuss condition for parallel resonance. So first of all, we are going to discuss about a AC parallel circuit. The AC circuit in which number of branches are connected in such a manner so that voltage across each branch is the same but current flowing through them is different are called AC parallel circuit. So these two methods can be used to solve the AC parallel circuit. So first method may be the phasor method, it is also called the vector method, and second is admittance method. So first of all, we are going to discuss about the phasor method. So here you can see in the figure that there is a two branches, one branch having a resistance R1 and inductance L, and second branch having a resistance R2 and capacitance capital C. So these two branches are connected in parallelly across the supply voltage V. So in branch 1, current I1 is flowing, and branch 2, that is a lower branch, current I2 is flowing. So total current that is flowing is I. So I is equal to what? I is the vector sum of current I1 and I2. So to apply the phasor method, there are different steps has to be followed. First step is what? Find the impedance of each branch of the circuit separately. So what is the impedance of the branch 1 which have resistance R1 and inductance L? It can be written as under root R1 square plus XL1 square, because XL1 is equal to what? 2 pi FL1, where L1 is the inductance connected in branch 1, and impedance for the second branch can be written as Z2 is equal to R2 plus XC2 square, where XC2 is equal to what? 1 upon 2 pi FC2. Second step is determine the magnitude of current and phase angle with the voltage in each branch. So as you know, the current flowing through branch 1 can be written as I1 is equal to V upon Z1. So because this is a AC current, so there will be some phase angle between voltage and current, and this phase angle can be calculated as phi1 is equal to tan inverse XL1 upon R1. Similarly, current flowing through branch 2 can be calculated as applied voltage, that is a capital V, divided by the impedance of the second branch, that is a Z2. So I2 can be written as V upon Z2. So now we have to find out the phase angle between current I2 and the applied voltage, and this phase angle can be calculated as phi2 is equal to tan inverse XC2 upon R2, where XC2 is capacitive reactance of the second branch and R2 is the resistance in the second branch. Step 3. Draw the phasor diagram by considering voltage as a reference phasor. Then represent the branch currents on it as shown in the figure. So here you can see, because it is a parallel circuit, so which quantity is the same for the all these two branches? So voltage, because in the parallel circuit branch voltage is same for the two branches, that means this voltage is common. So whatever the factor is common for the two branches, it should be taken as a reference vector. So we are considering voltage as a reference vector, which has been shown on the horizontal axis as you can see here. So now in branch 1 the current I1 is flowing, and then in branch there is a two component, or you can say two electrical elements are connected, that is a resistance and inductance. So as you know, the behavior of the RL circuit, in the RL circuit current lags behind the voltage by some angle, that can be written as phi1. So here you can see that I1 is making phi1 angle with respect to voltage V, and which is lagging in nature. In second branch, that is current I2 is flowing, which have two components, that is a resistance and capacitance. That means that branch is behaving like a RC circuit, and you can notice that in RC circuit the current lead by the voltage V, and how much angle will be there? It will depend on the value of the capacitance and value of the resistance. So here we are assuming that angle is phi 2. So here you can see that I2 is leading with angle phi 2 with respect to voltage V. Now you have to find out the current I. So this current I can be calculated with help of the phasor sum. Step 4, find the phasor sum of branch current by the method of component. That means all these two components I1 and I2 can be classified as a horizontal component and vertical component. So horizontal component can be written as I suffix xx, it can be written as I1 cos phi 1, and similarly horizontal component of current I2 can be written as I2 cos phi 2. Now you have to find the vertical component of these two currents I1 and I2, and this vertical component can be represented as I suffix yy. So here you can see that means vertical component of I1 is equal to what? I1 sin phi 1. It will be the downward, so it can be taken as a negative. That means it can be written as I1 sin phi 1 with negative sign. Now you have to find out the vertical component of current I2. So it can be written as I2 sin phi 2. So Iyy is equal to what? Minus I1 sin phi 1 plus I2 sin phi 2. So now you have to find the current I, total current I. So how you can calculate the total current I? Now you have a two component, horizontal component and vertical component. Just you have to apply the Pythagoras theorem. So what you will do, just you square the Ixx and square the Iyy and you add this and you take the under root. So I can be written as under root Ixx square plus Iyy square. Here you can see that I is also lagging with angle phi. That means it is this total current I is lagging with angle phi with respect to the voltage V. Step 5 is what? You have to find the phase voltage phi between the total current I and the circuit voltage V. And this phase angle phi can be calculated as phi is equal to tan inverse Iyy upon Ixx. So you have already calculated the component of Iyy and you have already calculated the component of Ixx. Just put the value in this expression so you can easily find out the phase angle. Now as you know, the power factor can be written as power factor is equal to what? Cos phi. So you have already the value of the phi. So you can also calculate the value of the power factor, which can be expressed as cos phi. And phi is equal to what? Phi is equal to tan inverse Iyy upon Ixx. Power factor can also be calculated as power factor is equal to Ixx upon I, where Ixx is the horizontal component of the current and this I is the total current. Now we have to understand some other parameters or terminology. First of all, we have to understand what is a conductance. The base of an admittance triangle is representing conductance as shown in the figure, and this conductance can be shown by the small g, and this small g can be written as y cos phi, where y is what? Y is the admittance of the circuit. So y can be written as 1 upon z, that means admittance is a reciprocal of the impedance. So that means y can be replaced as 1 upon z. And what is the value of cos phi? Cos phi can be written as r upon z. So just put the value here. So g, that means small g, or you can say conductance, can be written as r upon z square. And z square can be written as r square plus x square, where r is the resistance of the circuit, x is reactance of the circuit. This x may be the summation of the inductive reactance and capacitive reactance. So conductance is always positive irrespective of the circuit parameter, and the unit of conductance is mho. Next terminology that we have to understand, that is called susceptance. The perpendicular or an admittance triangle is representing susceptance as shown in the figure. So with the help of that triangle, you can calculate the value of susceptance. So this susceptance that is denoted by small b can be written as y sin phi, where y is what? Y is nothing but it is a admittance of the circuit. So y can be written as 1 upon z, and sin phi can be written as x upon z. So this small b can be written as x upon capital Z square, where Z is the impedance of that circuit, and this Z can be written as under root r square plus x square. So Z square can be written as r square plus x square. So this small b can be written as x upon r square plus x square. So here you can notice that susceptance is positive for capacitive reactance and negative for inductive reactance. The unit of susceptance is also mho, just reciprocal of ohm. Now second method by which you can solve the parallel circuit, that is called admittance method. Here you can see in the figure that in branch 1 there is one resistance R1 is connected in series with capacitance C1. In branch 2, in which current I2 is flowing, there is a two element, that is a resistance R2 and inductance L2. These two elements are connected in series. So branch 1 and branch 2 are connected in parallel, and across these two branches the supply voltage V are connected, and total current I is flowing in this circuit. This total current I is the algebraic sum, or you can say phasor sum, or you can say vector sum of I1 and I2. So for the admittance method, first of all you have to find out the impedance and phase angle of each branch. So what is the impedance of first branch? It can be written as Z1 is equal to under root R1 square plus XC1 square, and XC1 can be calculated as 1 upon 2 pi FC1. So that means now you are able to calculate the impedance. Now you have to find the phase angle in branch 1. So phase angle in branch 1 can be calculated as phi 1 is equal to tan inverse XC1 upon R1. So and XC1 can be written as 1 upon 2 pi FC1, because you have a value of C1. So just you have to put the value of frequency, you have to put the value of capacitance, so you can easily calculate the value of capacitive reactance. So now you have calculated the impedance of branch 1 and phase angle of branch 2. Similarly, you have to calculate the impedance of branch 2. So impedance of branch 2, which have resistance R2 and inductance L2, can be calculated as Z2 is equal to what? Under root R2 square plus XL2 square. And this phase angle in branch 2 can be calculated as phi 2 is equal to tan inverse XL2 upon R2. So where XL2 is equal to what? Omega L2, that means 2 pi FL2. And second step is what? You have to find the conductance, susceptance and admittance of each branch. So this conductance G1 for branch 1 can be written as R1 upon Z1 square. Susceptance B1 can be written as XC1 upon Z1 square, which is a positive. So Y1, that means admittance of branch 1, can be calculated by this formula, that means under root G1 square plus B1 square. Similarly, you can find out conductance of branch 2, that is G2, can be written as R2 upon Z2 square, and susceptance of branch 2 can be calculated as B2 is equal to XL2 upon Z2 square, which is negative. So admittance of branch 2 can be written as under root G2 square plus B2 square, where G2 is conductance of branch 2 and B2 is susceptance of branch 2. Now what you have to do, you have to find the algebraic sum of conductance and susceptance. So you have a two conductance, that is G1 of branch 1 and conductance G2 of branch 2. So this total conductance capital G can be written as G1 plus G2. Similarly, you can calculate the susceptance of the total circuit, that means it can be denoted by capital B. It can be written as B1 minus B2. So you have calculated the total conductance and total susceptance. Now you have to find the total admittance of the circuit. So total admittance of the circuit can be written as Y is equal to under root G square plus capital B square. Then what you have to do, you have to find out the branch current and the total current. So branch current can be calculated as I1 equal to applied voltage, that is capital V, multiplied by admittance of branch 1, that is Y1. So I1 is equal to what? Capital V multiplied by Y1. Similarly, you can calculate the branch current for second branch, and this can be calculated as I2 is equal to what? V into Y2. Now you have calculated the two branch current, that is I1 and I2, and now you have to calculate the total current flowing through this circuit, that is a capital I, and this capital I can be written as total voltage V multiplied by the admittance of the circuit, that is Y. So total branch current of the circuit can be written as I equal to V into Y. Then you have to find out the phase angle and the power factor of the whole circuit. So phase angle can be calculated as phi is equal to tan inverse capital B divided by G, and similarly you can calculate the power factor, because as you know power factor is nothing but it can be written as cos phi. So you have already calculated the phase angle of for this circuit, so just put the value of phi here. So you can write power factor is equal to cos phi, or you can say cos tan inverse capital B upon G, or you can say power factor is equal to capital G upon capital Y. Now the next topic that we are going to discuss, that is parallel resonance. So here you can see this figure represents a parallel resonating circuit where a coil is connected in parallel with the capacitor C, and the combination is connected across an AC voltage source of variable frequency, that is a F. So here you can see there is a two branch 1, in middle one you can see there is a coil, and coil have a resistance R and inductance L, and there are another branch in which current flowing, that is I suffix C, which have a only capacitance, that is a capital C. So there is a two branch, one having a coil which have resistance and inductance, and another branch have only capacitor only. So here you can see that IC is what? IC is the current through the capacitor. What is the IL? IL is the current through the coil. And what is the I? I is the vector sum of IL and IC, that is the source current. And V, capital V is the supply voltage. The BR is the voltage drop across resistance. V suffix L is the voltage drop across inductance. B suffix C is the voltage drop across capacitance. And phi is the power factor angle of the coil, or you can say the angle of the lag of IL with respect to applied voltage, or you can say supply voltage capital V. This Z suffix L is the coil impedance, and X suffix C is the capacitance of the circuit. So here you can see that in the phasor diagram, that is a voltage B has been taken as a reference vector, which has been shown on the horizontal component V, and there is a current, charging current, you can say capacitive current IC, because there is a pure capacitor. That means this capacitive current will lead by the 90-degree with respect to the voltage, and in the coil that current has been shown as I suffix L. That means in this branch there is a two element, that is resistance and inductance. So of course there will be a current which will be lagging in nature, which lag with respect to the voltage B with angle phi. So it is denoted here, IL is lagging with respect to V by angle phi. So now you have to take the component of this IL, that means horizontal component and vertical component. Horizontal component of this IL can be written as IL cos phi, and vertical component can be written as IL sin phi. So in parallel resonance condition, what is the condition? The IC is equal to IL sin phi, or you can say current flowing through capacitance is equal to the current flowing through coil vertical component of current of IL, that is IL sin phi. So now you have to find out this capacitive current IC. So as you know, because voltage is applied across two branches, so that means this voltage is same. So this IC can be written as V upon XC, where XC is the capacitive reactance of the branch 1. So at resonance, the capacitive current must be equal to the inductive part of the coil current, that is the imaginary component of IL and IC must cancel each other at resonance condition. So you can write like this: IC is equal to what? IL sin phi, where sin phi can be written as XL upon ZL. So just put the value of IC. You have already calculated the value of this capacitive current IC. This IC can be written as voltage V upon Xc, and IL can be written as V upon ZL, and value of sin phi can be written as XL upon ZL. So after the solving, you will get ZL square is equal to Xc into XL. That means this ZL square can be written as Xc into XL. And you can calculate also ZL square is equal to 1 upon omega naught C multiplied by omega naught into L. So this omega naught will be cancelled out from the numerator and denominator. So ZL square can be written as L upon C, or in another words you can write ZL is equal to under root L upon C, where this omega naught represents resonance frequency. So this can be written as Z square can be written as R square plus omega naught square L square under root is equal to under root L upon C. So this can also be written as, if you are square the both the side, left hand side and right hand side, so you can write omega naught square L square is equal to L upon C minus R square. Again you can write this expression omega naught square is equal to 1 upon LC minus R square upon L square. Now how you can write this omega naught? This omega naught can be written as under root 1 upon LC minus R square upon L square. Here what you will do, just you multiply it by inductance L in numerator and denominator in the first term, that is 1 upon LC. So it can be written as L upon L square C square minus R square L square. So this L square can be taken outside. So you can write omega naught is equal to 1 upon L under root L upon C minus R square. So F naught can be written as 1 upon 2 pi L under root L upon C minus R square. If the resistance of the coil be neglected, then resonance frequency for this parallel circuit can be written as 1 upon 2 pi L under root L upon C. So if you take L inside of the under root, so it can be written as 1 upon 2 pi under root LC. So again at resonance, since the reactive component of IL and IC balance each other, the only remaining part of the current is equal to what? It is equal to IL cos phi. So this total current I can be written as IL cos phi, where I is equal to what? I is equal to V upon Z, and IL can be written as V upon ZL, and cos phi can be written as R upon ZL, where this Z is equal to what? It is the equivalent impedance of the parallel circuit. So this Z can be written as ZL square upon R, and you can replace ZL square by L upon C. So just put the value here. So Z can be written as L upon CR. Then the equivalent impedance of the parallel resonating circuit is L upon CR at resonance. So in case of the series resonance, what is the impedance of the circuit? That is equal to R. But in case of the parallel resonance, impedance of circuit is equal to what? L upon CR. This impedance is called dynamic resistance of the parallel circuit. Normally R being less, this impedance is very high at resonance, and then current is much lower in the parallel circuit. Then this circuit is also called rejector circuit. Now we have to understand the resonance curve. Here you can see the resonance curve. Since admittance is minimum or impedance is maximum at resonance frequency omega naught, so current I is also minimum at parallel resonance. Now we have to understand the properties of the resonance of parallel RLC circuit. So you can notice that power factor of parallel RLC circuit at resonance condition is unity. And second property you can notice here, the current at resonance is equal to B upon L upon CR and is in phase with the applied voltage. The value of current at resonance is minimum. And third property is what? Net impedance at resonance of the parallel circuit is maximum and equal to L upon CR. The next property that you can notice here, the admittance is minimum and the net susceptance is 0 at resonance. The resonance frequency of the circuit is given by F naught is equal to 1 upon 2 pi under root 1 upon LC minus R square upon L square. Now we have to compare the condition for the series resonance circuit and the parallel a resonance circuit. So here you can see in the first column there is some particulars are given. In the second column the series resonance RLC circuit are considered, and the third column parallel RLC circuit are considered. So here you can see impedance at resonance in case of series RLC circuit is minimum, in case of parallel RLC circuit it is a maximum. If we are talking about the current at resonance, that in series RLC circuit, so it is a maximum because net impedance of series RLC circuit is equal to the only resistance, because inductive reactance is equal to the capacitance, capacitive reactance which will be cancelled out. So net impedance of the circuit is equal to the only resistance. So impedance is reduced, that means current is increased. So in case of series resonance, maximum current will flow when it is in resonance condition. But in case of parallel RLC circuit, the current at resonance condition will be maximum. And if you are talking about the effective impedance in series RLC circuit is equal to the resistance. If we are talking about the parallel RLC circuit, it is equal to L upon CR. Because in both the cases the current is in phase with the voltage, that means phase angle is 0. If phase angle is 0, that means cos phi is 1, that means power factor is unity in both the case series RLC circuit, in parallel RLC circuit if it is at resonance. And for resonant frequency for series RLC circuit can be written as 1 upon 2 pi under root LC. For parallel RLC circuit it can be written as 1 upon 2 pi under root 1 upon LC minus R square upon L square. Series resonance RLC circuit, it magnifies the voltage, but in case of the parallel RLC circuit, it magnifies the current. And in case of series RLC circuit, the magnification is equal to omega L upon R, but in case of parallel RLC circuit, magnification is omega L upon R. Now we are going to discuss some example which is based on the parallel resonance. So as you can see in the figure, you have to find the value of resistance R so that the condition for resonance is fulfilled. So here what you can write, admittance of first branch can be written as Y1, which can be written as 1 upon R plus 5j. So just you multiplied R minus 5j in numerator and denominator. So this Y1 can be written as R minus 5j upon R square plus 25. Similarly, you can write admittance of second branch, which can be written as Y2. It can be written as 1 upon 4 minus 3j. Just you multiply it by 4 plus 3j in numerator and denominator. So this Y2 can be written as 4 plus 3j upon 25. Now because it is a parallel circuit, so in parallel circuit, if you want to calculate the equivalent admittance, so in case of parallel circuit, admittance of the two branch can be added directly. So Y can be written as Y1 plus Y2. So it can be written as R minus 5j upon R square plus 25. Similarly, Y2 can be written as 4 plus 3j upon 25. So according to condition of the resonance, the imaginary part of admittance must be 0. So you can write minus 5 upon R square plus 25 plus 3 upon 25 is equal to 0. Or in another word, you can write 5 upon R square plus 25 is equal to 3 upon 25. So after solving this expression, you can calculate the value of resistance, and this value of resistance is equal to 4.082 ohm. Now we are going to discuss another example. Here you can see a coil of 15 watt resistance and 0.3 Henry inductance is connected in parallel with a variable capacitor across a 230 volt 50 Hz supply. You have to calculate capacitance of the capacitor for the resonance, second effective impedance of the circuit, and third current supplied from the mains. So according to the given data, just you draw the circuit like this. You draw the resistance R 15 ohm is connected with inductance L equal to 0.3 Henry, and there is a one variable capacitance are connected across this coil, and 230 volt 50 Hz supply is connected across these two branches. So resonance frequency can be written as under root 1 upon 2 pi 1 upon LC minus R square upon L square. So you can write this expression as equal to 1 upon LC equal to 4 pi square FR square plus R square upon L square. Just put the value of the different parameter given in this question. So after the solving, you can find out the value of capacitance, which is coming equal to 32.94 microfarad. Now you have to calculate the effective impedance of the circuit. So effective impedance of the circuit at the resonance is equal to what? This ZR is equal to L upon CR. Just put the value of L, C and R. So after the putting the value and calculating this value, you are able to calculate the effective impedance of the circuit. ZR is equal to 607.18 ohm. Now you have to also calculate the line current. This line current can be written as IR is equal to V upon ZR. Why I am writing I suffix R and Z suffix R? Because we are talking about the resonance condition. That's why I am writing this current IR. So IR is equal to what? V upon ZR. So supplied voltage is given as 230 voltage and ZR is a impedance at the parallel resonance. You have already calculated. This ZR is equal to what? 607.18 ohm. So just after the putting this value and after the calculation, you get the value of line current is equal to 0.3788 ampere. So dear learner, in this particular session, we have discussed about the parallel connection of the RLC circuit. How do you calculate the impedance? How do you calculate the admittance? How do you calculate the phase angle of in different component if resistance, inductance and capacitance are connected in parallel. And we have also discussed about the resonance condition for the parallel circuit. Thank you very much.